All right, I'm going to start going live here in a second, and we're going to open this up.
Great. Okay. So folks will start coming in on Zoom and on YouTube. So welcome everyone who's coming in. So folks on YouTube, if you were waiting in the original version of the stream, you may have seen a brief video of me looking very confused. That was due to a little glitch with our streaming setup. Apologies for that. To everybody who didn't see that, good. But welcome back to the Weights and Biases Salon, to the first Salon of 2021. I'm excited. I feel like I say this about all the salons, but I am very excited about this salon. We have Greg Yang on here from Microsoft Research AI, who has been doing some work in this series of papers. The tensor program series has culminated in this really exciting work on infinite width neural networks that can actually learn features and outperform finite width neural networks, which is something that's been in some ways 30 years in the making since Radford Neal's early papers on the subject. So I'm really excited to hear him talk about it and to get questions from folks. So right now, the way that folks in the audience, for folks who haven't joined a webinar like this before in Zoom, the way to ask questions is through the Q&A button. So you can type your questions there, and I'll make sure that those get relayed to Greg. All right, so if you have any questions, I believe you might also be able to ask questions, yes, via the chat. So ask questions via the chat, either on YouTube or on Zoom, and we'll get any technical issues squared away or ask questions. All right, Greg, go ahead and take it away.
Yeah, thanks for the introduction, Charles. So also let me know if there's any technical difficulties. My internet today has been kind of unstable. So or I guess I might not be able to hear you if there's technical difficulties. But anyway, so we'll just keep going forward. Yeah, so I'm really honored to be featured here today, hosted by Charles. And yeah, like he introduced, I'm going to talk about feature learning infinite width neural networks. And I'm gonna just dive straight into it. So the plan for today are couple-fold. So we're gonna first talk about why pre-training transfer learning requires feature learning. Then we briefly review some of the current theory revolving around your tangent kernel. And then we'll talk about our proposal, which is the feature learning limit of neural networks. So pre-training and transfer learning is very successful in deep learning. And there's no more prominent examples than ImageNet, ResNet on the image domain, and BERT GPT-3 and so on the NLP domain. And in both cases, pre-training and transfer learning cannot happen without feature learning. And before I explain why I say this, which might come as really obvious to some of you, but might be more needs more justification for others. So before I justify it, let me just be very straight about what I mean by feature learning in this talk. So any neural network, you can express the structure of the neural network as simply a composition of two functions. The first function is a nonlinear embedding function from input space to like the hidden layer of the neural network. And then there's another linear map from the hidden layer, which you can think of as embedding space, to the output space, which usually is like the label space, right? Like, so you output a logics over labels, and then via softmax, you can output probabilities. So by feature learning, I mean the embedding function is learned. And just to briefly review how the pre-training and fine-tuning paradigm right now works. Right now, during pre-training, you train a really large model on a very large data set. Sorry, somebody raised their hand. I don't know if I should. So is the paradigm that I should respond immediately, or?
So if you have a question, rather than raising your hand, just put it in the Q&A or the chat. So folks in the audience, go ahead and do that.
All right, cool. So I'll just keep going, right? So yeah, during pre-training, for example, ImageNet and GPT-3, during pre-training, you train on a very large data set from a general domain, usually without a lot of labels. For example, in the GPT-3 case, but in ImageNet, you do have a lot of labels. But you train on a very large data set, and then during the transfer stage, you you care about this like actually very specific subdomain where you want to apply your model to, and you collect very expensive but well-labeled data in that domain, and then you apply your pre-trained data, pre-trained model, and then you train it a little bit on the small data set. And usually what you find is that the performance of such a transfer network is much, much better than if you train from scratch on this small data set from the get-go. And the way we usually do this is first we discard the readout layer from the pre-training. So just to be clear, readout means like this linear layer that goes from the last hidden layer of the neural network to the output space. So you discard this layer, and this is just because during pre-training you usually have a different objective and different output space than the downstream tasks you're actually interested in. So just kind of like for type checking reasons, you have to discard it anyway. And there are two very popular ways of doing this fine tuning. So in the linear fine tuning case, you just train a new readout layer of the right type, right? Like if you want to classify cats and dogs, you would train a new layer with output dimension 2. So it's very easy to see that if pre-training improves linear fine tuning, then the embeddings, i.e. the features of the inputs, must change during pre-training, right? I mean, like the fine-tuning stage is entirely a linear problem. It only depends on the performance, that only depends on the embeddings, the quality of the embeddings. So this, in this particular case of linear fine-tuning, this justifies why I say that transfer learning really requires feature learning. There's another popular way of doing fine-tuning, which is called total fine-tuning, where you train the entire neural network, not just the last layer. You can actually get the same conclusion, though the logic is a bit more involved. So I won't go into detail here, but the point is that in the end, my point stays that transfer learning really requires you to do feature learning. All right, so now let's look at how current theory deals with transfer learning or feature learning. So one of the most popular theories nowadays is called this thing called neural tangent kernel. The idea is actually very simple. So we take the neural network function f of x with parameters data, and we just do a naive first order Taylor expansion around the initialized value. I don't know if you can see my mouse cursor or not. But
yeah, it's visible.
Yes.
Yeah,
Should I? What should? You can see it. Okay. Yeah, and so you do a first order Taylor expansion, and you can write this difference of essentially the change in the neural network due to changing the parameters as this inner product between the gradient of f with respect to the parameters and the change in the parameters. And you can rewrite this as a kernel equation where the change of f in the function space is equal to essentially a kernel times the loss derivative, and the kernel is this kernel induced by the gradient of the function evaluated at the initial parameters. So the really nice thing about this, of course, is that you essentially have linearized the really complicated dynamics of training a nonlinear neural network. And as a result, if essentially in this particular framework, if you look in the function space, then the optimization landscape actually becomes convex, kind of like this figure, this animation illustrates. And theoretically, this is easy to analyze, and we can obtain a lot of optimization generalization results. Really, I think for the first time for really complicated neural networks that was not really in reach before. So from a theoretical angle, this is actually a very significant framework to think about neural networks, large neural networks. But the very crucial drawback of this framework is that this particular NTK limit does not learn features. So pre-training is no better than random initialization in the NTK limit. So, this statement, again, could be really obvious to some of you, but some other of you might require some justification. So let me do that very quickly. So again, we have the first order tail expansion framework for NTK. And of course, first order tail expansion really only works if the change in the parameters here is not very large, right? So if NTK describes actual neural networks, then it must be the case that theta minus theta 0 is small. But then this implies that the embedding function cannot change too much, which implies that essentially the features don't change, right? So this is just like a very, very simple intuition about why in the NTK limit you do not have feature learning. Of course, like the real math is a bit more complicated than that. But here's a very vivid example to show that the NTK limit doesn't learn features. So in this example, I trained word-to-vec embeddings of a bunch of different words, but here is US words corresponding to US cities and states. And I did a PCA of the learned embeddings into a two-dimensional space. And the models I trained here are, well, first with 64, so a 64-dimensional embedding word-to-vec, just like the conventional word-to-vec. On the left, I computed the same thing for the NTK limit. So essentially, like the theoretical limit of the entire word-to-vec training procedure in the NTK limit. And then on the right, I did the same thing. Essentially, I took the feature learning limit, which I'll describe later what exactly is meant by this. But I took the feature learning limit of the word-to-vec training procedure, the neural network, and the resulting infinite width embeddings are projected into 2 dimensions via PCA. And the thing you should take away from these plots is that whereas in the NTK case, the two types of words, US cities and US states, are essentially like all mixed together in the 2D space. In the finite width case with 64, you can see some natural separation between the two types of words, indicating that the geometry of the word embedding really encoded some semantic information of the words. And furthermore, in the infinite width case, you have an even more clean natural separation between the two clusters, the two types of words, compared to the finite width case. So this kind of indicates that one, NTK is not the right limit to take to understand feature learning, which was made very obvious by the contrast between the first plot and the second two plots. And two, the feature learning limit that I'll describe very quickly, very soon, will be a very natural notion of feature learning, as you have this kind of natural increase in the semantical content of the learned word embeddings.
A quick question, Greg, from the audience.
Yeah.
So is the neural tangent kernel the only sort of kernel that you can use there? Are there other potential choices there?
Yeah, good question. So essentially, it doesn't matter which kernel it is, as long as in the kernel style limit, you're gonna get the same thing. So it doesn't depend on what the kernel itself is. It's just that as soon as you have a kernel, it doesn't work. So I'll talk about actually very quickly, a bit later, essentially you have a dichotomy between kernel limits, just like the NTK, and you have the other categories of feature learning limit. And essentially, like any natural, in some sense, natural limit of a neural network is either one of them, but we cannot have both. So if you want to do feature learning, then it's definitely not a kernel limit. Okay, so let me move on. Okay, so let me just give you one more quick plot on some numbers, concrete numbers on Word2Vec. So in Word2Vec, you learn these embeddings, but you can, of course, you want to use them actually downstream, and you can use them in very many different ways. But academically, a very common evaluation task is OR analogy, which asks this kind of famous question: what to a queen is a man to a woman. It sounds real philosophical, but it's a collection of these analogy questions that you use the word embeddings learn to answer via some algebraic manipulations. But I'm not going to talk about the details how the actual evaluation is done, but let me just highlight some numbers. In the plot here, we evaluated a bunch of different Word2Vec embeddings. Well, for the final ones, we have width or dimension embedding from 2 to the 6th power to 2 to the 10th power. And then we have the infinite width feature learning limit that I'll explain very soon. And then finally, we have the NTK limit. So there are a couple different takeaways. First is that the NTK limit, of course, has essentially zero performance on word analogy. And like I said, that's because NTK doesn't really learn anything. The word embedding is essentially random. Like it's just the same, essentially, from as the initialization of the training procedure. So, like during evaluation, you're essentially just doing random guessing. And because the number of words is so large, when you do random guessing on this plot, you cannot actually see the real number. It's just essentially the same as zero. And in contrast, of course, like finite width and infinite feature learning Word2Vecs have non-trivial performances. And then the other thing you can notice is that on the x-axis, I have the epoch. So this is the training time of the models. And you can see that as width increases, which corresponds to color becoming darker, at every point in the training procedure, the wider the model is, the better the training performance. And actually, sorry, this is the y-axis is actually the evaluation on downstream tasks. So it's actually like test performance. But what I'm saying here is that at any given time during the training, if you take that partially trained model, and evaluate it on the downstream task, you see a uniform increase in performance as the width increases. So this indicates that this feature learning limit that I'm about to introduce to you is the right notion. It captures feature learning in a meaningful way, such that as width increases, the performance also increases, and presumably the features learned actually becomes more and more meaningful. We also have similar results on meta learning on mammal, but I mean essentially the takeaways are the same, so I'm not going to actually talk about it in this talk. All right, so now we'll get to the juicy part where we actually talk about the feature learning limit. So before I begin, let me just give you some way to frame this, to think about the different kinds of possible limits. And I think the right way to think about it is that for any finite neural network, when you write PyTorch code, you assume some parametrization of your neural network, right? I mean, like just as concrete examples, when you write PyTorch code, you use by default like Lacoon initialization, so like fan-in initialization, and every such parameterization induces some kind of infinite width limit or infinite width training dynamics. If you just naturally just change your width number in your code from 1,000 to 10,000 to 100,000 and so on and so forth, assuming you have the compute to actually run this computation, then the dynamics of your neural network will actually converge to something as you increase that width number in your code. So my point here is that every parameterization corresponds to an infinite width dynamics. And the feature learning limit that I've been talking about, and I'm going to be more concrete on, is induced by this thing we call the maximal update parameterization, which I'll describe shortly. But just before that, let me quickly give you a big picture of what's going on. So in general, you have a lot of different parameterizations. And there's a way to formalize this into something called ABC parameterizations, but I'm not going to go into details about this in this talk. I'll briefly give you some pointers later. But you have the space of possible parameterizations, which includes, the neural tangent parameterization and the standard parameterization, like the Lacoon initialization, whatever you use in PyTorch, or mean field parameterization, which is more relevant in the theoretical literature. Most of them are going to induce unstable or trivial limits, in the sense that like training dynamics in the infinite width limit will blow up, or like the neural network, the infinite width neural network will not move during training from initialization. But within those that are stable and non-trivial, most of them are going to be in the kernel regime, so they're going to induce kernel limits. So in particular, neural tangent is a prominent example, but also standard parameterization with the appropriate learning rate. But if you actually use a standard parameterization with a constant learning rate, things are actually going to blow up. So it's going to be unstable. And the maximal update parameterization that I'm going to introduce next is essentially like this vertex in this very small region that actually does feature learning. And this being a vertex means that it's maximal in some sense. Colloquially, you can understand this as saying that if there's features to be learned, it learns the features. Okay, that's all I'm going to say about this, the big picture. Now let me drop down into something concrete. Let me tell you about the maximal update parameterization, which is abbreviated as mu-p. So let's be very concrete. I'm going to tell you what this parameterization actually is. And the easiest way to understand this is to modify the standard parameterization to get maximal update parameterization. So you need to make two changes to the standard parameterization. And I'll tell you about why, intuitively, why we need those changes. But the first change is in the last layer. And the reason why we need to make that change is because in standard parameterization, the last layer, essentially, one is too large initialization, and two, it gets too much gradient. And with this modification, essentially the purpose is to make the last layer a bit smaller, and also make its gradient a bit smaller. And this is so that you can use a larger learning rate, such that like all the previous layers get more gradient. Okay, so concretely what we do is we divide the largest by square root of n and use a constant learning rate. So you can see here, there's a 1 over square root of n factor at the end of the neural network. And the last layer weights are sampled the usual way using the Lacoon or fan-in initialization. And this alone suffices to enable feature learning. And let me remind you that in the standard parameterization, in the figure I just showed you, if you don't divide by square root of n, and you use a constant learning rate, essentially, as you train really wide neural network, the output of neural network will blow up, and as well as the pre-activation of the neural network will blow up. Okay, so second modification is in the first layer, and the intuition of why we need to make this modification is that in standard parameterization, the first layer actually gets very little gradient compared to the rest of the neural network. So, taking a slightly larger picture, essentially in the standard parameterization, the last layer gets too much gradient, the middle gets okay amount of gradient, and the first layer gets too little gradient. So we're fixing the problem in the first layer. The easy fix here is that we multiply the pre-activation by square root n, and we use fan-out initialization. So here's the square root n in the pre-activation of the first layer, and the weights are sampled like fan-out, right? So 1 over n, where n is the output dimension. So this will serve to increase the gradient by n. This is needed to enable feature learning in every layer. All other weights are initialized kind of the same way using fan-in initialization. Okay, so that's essentially the maximal update parameterization. Now, next part of the talk, most of it is going to be about giving you some intuition of how to compute this limit. The gist of the story is that you can essentially compute the limit for any neural network and essentially any algorithm. Like essentially, if you have a PyTorch code describing whatever you're trying to do, anything in deep learning, you can convert it systematically to a computation for an infinite width neural network and a way to compute that limit. But I'm going to focus very, very specifically on a one-hidden layer linear neural network as a motivating example. So I'll go into that very shortly. Now let me go one level deeper into the intuition of how to compute this. And this is given by this quote. When width is very large, every activation vector has roughly ID coordinates. So at any time during training, and using tensor programs, we can recursively calculate such coordinate distributions and consequently understand how the neural network function evolves. Okay, so if you have been doing some calculations with NTK, you might be familiar with the first sentence in the sense that initialization, every activation vector has roughly ID coordinates. But this is at initialization, not anytime during training. So I need to justify why at any time during training, every activation vector has roughly ID coordinates. And then I'll briefly touch on how we can recursively calculate such coordinate distributions. All right, so as a motivating example, let's look at linear one-hidden layer neural network. So assume input and output dimension are both 1. Then in the neural network can be represented by 2 essentially vectors, right? Because the input and output dimensions are 1. So the first layer, second layer weights are both vectors. And a forward pass is represented by essentially the multiplication of these 2 vectors times the input, which is a scalar. We're gonna have ID coordinates initialization, initialize accordingly, essentially the variance 1 over n, but we won't need that detail until later. Okay, so let's look at what happens in the first forward pass. Again, f is the scalar product of the 2 vectors times the input. And because it's a scalar product, the sum of a large number of roughly ID elements, which specifically are like first layer element times second layer element, right? And these things are ID across the width dimension. So as width becomes larger and larger, f of I will converge to something, to some deterministic number by law of large numbers, which in this specific case of a random initialization is just 0. Okay, so if f converges, then the loss derivative of f also converges, right? Usually because loss derivative is a continuous function. So if f converges, then this continuous image of f has to converge. All right, now let's look at the first backward pass. In particular, let's look at the gradients of the weights. So you can do a very simple calculation, but the point here is that the gradient of the second layer is essentially the first layer weights times these two scalars, the input times the loss derivative. And similarly, the first layer gradients of the second layer weights times these two scalars. And like I said, the scalars are roughly deterministic. I mean, xi, the input is essentially by definition is deterministic, and the loss derivative is deterministic because f converges and L prime is continuous. So the structure of this gradients actually implies that both layers gradients are approximately ID. So when you add the gradients to the weights via the first gradient step, you maintain this property that the weights have approximately ID coordinates. And something else we can observe is that, of course, like at this point in time in the second forward pass, the weights are linear combinations of the original weights from initialization, right? And this fact will be important for calculating the infinite width limit later on. But for now, we don't actually need it. Okay, so let's keep going forward and see what's happening elsewhere in the second forward pass. The computation of f again implies that it converges by law of large numbers because it's a sum of large number of ID things. And the loss derivative converges as well because f does. And again, the gradients have the same structure. That means that they have approximately ID coordinates. And when you update, the weights remain roughly ID. So so this logic, obviously repeats for all times. And this justifies what I said earlier about how when the width is large, every activation vector has roughly ID coordinates at any time during training. And the stress is on at any time during training, right? All right. Now, earlier I also said that weights at any time are linear combinations of weights from initialization. And this is already hinted at by the calculation we did earlier. And using this observation, we can see how to calculate the infinite width limit without resorting to an actual neural network. So let me just give you an overview of what is involved. So let me establish some quick notations. I'll let U denote the first layer weights and V denote the second layer weights. And in particular, without the subscripts, I'm gonna just use them to denote the initialized values, so the random initialization of the weights. And initialization, they're sampled with variance 1 over n, where n is the width. Okay, and additionally, another piece of notation is that during the t+1 forward pass, you're going to use subscript t to denote the particular values of u and v at that time. So when I say weights at any time are linear combinations of weights from initialization, this implies that for any t, there are coefficients at, bt, ct, dt, which converge roughly deterministically, such that we can write vt equal to at times v plus bt times u, ut equals ct times v plus dt times u, where again u and v without subscripts are denoting the initial values of the weights. And of course, when t equals 0 initialization, AT and DT are 1, and BT and CT are 0. Sorry. Okay, so with that said, we can look at what happens during the t+1 forward pass. And essentially via the same kind of law large number intuition, we can see that f of xi equals AT times CT plus BT times DT times xi. And this is, you can get this by just kind of expanding the product of VT times UT and noticing that because U and V, again, they refer to the initialized values. U and V are independent, so there's no correlation between the UV and VU cross terms. So the only terms that survive are via contracting V with V and U with U, and that results in the terms AC and BD. And then we can investigate the t+1 backward pass, and along the same lines of what we did before, we can notice that the gradients are also linear combinations of the initial U and V's, right? In particular, they take these particular forms. And when you make the updates, now it's very apparent how the A's and the B's, the C's and T's will update after this particular time, like so. Okay, so I hope this convinces you that you can repeat this logic over and over. And the point here is that to compute this infinite width limit, you only need to compute the values of A and B and C and D across time. And if you want to train for 1,000 steps, you just have to calculate what the values of A, B, C, D at time 1,000 is. And you can do this via these recursive formulas. And they're summarized here. So again, we're in the context of this linear one-hidden layer neural network for illustration purposes. And here we have the input and output dimension equal to 1 and learning rate equal to 1. And then in the infinite width limit, we have that at any time, the function, the neural network f is equal to AC plus BD times the input xi, where A, B, C, D are updated like so, with the initial condition that A and D are 1 and B and C are 0. All right, so if you've been paying a bit of attention, then you might notice that this looks awfully like a linear one-hidden layer with two neural network, where the hidden dimension correspond to AB and CD. So in particular, AB are the second layer weights, and CD are the first layer weights. But in contrast to how people usually train their neural networks, what's different is the initialization. So here we have some kind of quote-unquote diagonal initialization, which can be summarized by this matrix equation, in contrast to random initialization that people usually have. So we can summarize this whole box as this kind of like psychological equality. So in other words, feature learning limit of a linear one-hidden layer neural network with random initialization is equivalent to a with D in plus D out linear one-hidden layer neural network with diagonal initialization. So we instantiated this with D in D out equal to 1. But this is in general true for any input and output dimension. We can generalize this logic very easily. And in fact, this equality is essentially what we use to compute the large scale experiments like Word of Vec. And just to be very concrete, in that particular example of Word of Vec, D and D out are the vocab sizes, which are like 140K to 280K, depends on the data set. All right, so let me just summarize what we've been through just now. in the one-handed layer case, the weight matrices have IID coordinates initialization. The function output converges due to law of large numbers. Gradients have approximately IID coordinates. So after gradient update, weight coordinates are still approximately IID. And then you can repeat this logic. So this should convince you that the weights at any given time have approximately IID coordinates. But of course, like they're going to be correlated across weights. And then in the linear case, we can express the weights at any given time as linear combinations of weights from initialization. This allows us to have efficient calculation of the limit. All right, so that was one-handed layer. Let me give you an appetizer for the deeper case, where the math will actually significantly become more complex. So I don't have any room to give you the full course, but an appetizer should suffice. So the main difficulty here is that you have this n times n Gaussian random matrix W in the middle network, which comes from the random initialization of weights. So it has two kinds of behaviors that you have to keep track of. One is the central limit behavior, which is essentially something you're familiar with if you have done NTK calculation before. But essentially here, if x is a vector independent of W, then Wx is a Gaussian vector. The other thing is that you have to be careful about how W correlate with W transpose, right? Like during SGD, if you use W in the forward pass, then you have to use W transpose in the backward pass. So this correlation actually doesn't matter so much for the calculation of NTK, because that only depends essentially on the first backward pass. But if you do more than one step of SGD, you'll see this occurring. So it's important to kind of be careful about both of these behaviors and kind of keep track of them in a systematic way. And that's by no means a trivial thing. And this series is called Tensor Program Series, and there were like 3 papers, 4 if you count the 0th paper, I guess, before this. And the crux of the mathematical foundation is to deal with this complexity here. Yeah, and in the framework, this tensor program machinery essentially automates all of these derivations. So essentially, even if you don't know anything about probability theory, you can just read the machinery as an algorithm, and as an engineer, you can just implement this and can automatically translate between PyTorch code and infinite width neural networks. I'm almost done, but let me just highlight some other results in the papers, so to give you some pointers if you're interested. We isolate a natural class of parametrizations, which I briefly mentioned before as the ABC parametrizations, which contains the NTK mean field standard parametrizations, as well as the maximum update parameterization I introduced here. We classify these parameterizations essentially into either feature learning parameterization, which induces a feature learning limit, or kernel parameterization, like NTK, but you cannot have both. So it's a dichotomy. And this gives you some interesting consequences. One is that certain functional dynamics are not valid infinite with limits. So in other words, it's not like if you just grab something from the bag, some kind of dynamics, some functional dynamics, but then there's a neural network that corresponds to that in the infinite width limit. Now, that's not the case. And I give you some concrete examples. For example, higher order generalizations of NTK dynamics. So I think this example is actually very pertinent because a lot of people after the NTK paper essentially just try to expand more terms. Instead of first order Taylor expansion, you do higher order Taylor expansion. And they're saying that essentially like doing that doesn't give you valid limits. And another interesting consequence is that any feature learning limits function values must be 0 everywhere initialization. So this contrasts with For example, in the NTK limit, the initialization is a GP, is a Gaussian process in the infinite width limit. And what this is saying is that if you have a Gaussian process initialization, that means your last layer initialization is too large. And this prevents you from using a large learning rate to make the body of the network learn features. So you should initialize so that the last layer is smaller, and then you use a larger learning rate so that the features are learned. Okay, so that's it. I'm going to end here, and here are some QR codes to the paper and a longer 2-hour talk with more details in case you're interested in further. Yeah, thanks, and I'll take any questions you have.
Great. I've got lots, but folks in the audience, feel free to put them in the chat. The thing I wanted to start off with, I think, was, so you noted that the standard parametrization that everybody uses is unstable, that you can't essentially take an infinite width limit with it. Do you think that that's something, that's actually a benefit for working with finite width networks? Or do you think that switching over to a parameterization like the maximal update one, scaling down our logits, scaling up our inputs, do you think that's something that would actually make this, like, finite width neural networks have better properties, perform better?
Yeah, it's a good question. So this is also, it's a good question, but it's also a very subtle question. And in some sense, it requires a paper to answer, and that's what's coming next in the series. But let me give you at least like some overview or like some of the punchlines, perhaps not into details, but some vague punchlines. So I say it's a subtle question because if you fix your width, like your width is finite, then really like all the parameterizations are the same up to constants, right? Like, because if your n is a finite number, then you can insert constants in front of like the 1/n or whatever, such that you can just go between different parameterizations very freely. And as an aside, like everything I talked about here, I say like 1/n or something. Really, the thing that matters is the scaling with n. And I say 1/n because I want to simplify the presentation. But in practice, if you want to implement these, like the constants in front of the 1/n and whatever power of n is actually very important. So if you put all those constants in, then like I said, you can essentially go between all the different parameterizations as soon as you fix the width, right? And what is important and what is important indicated by all of this this material is not that one parameterization is better than another one if you fix the width, but rather if you fix the parameterization and you let width go to infinity, then one is better than another, right? Like it's a scaling behavior that really matters. So maybe this is a roundabout way of answering a question, but this is what I mean by subtlety. And so you cannot make a statement, or it kind of doesn't really make sense to make a statement saying, oh, one parameterization is better than another parameterization for a particular finite width neural network in the context of this kind of parameterization where I'm really talking about scaling with width. But you can talk about certain things you cannot do before, but you can do now if you use these kind of parameterizations. So as a sneak peek, the next paper will be talking about the benefits of maximal update parameterization over any other kind of parameterizations, enabling you to do things that you probably didn't think it was possible before by doing so. So okay, so that was a long version, but the short version is yes, you should use maximal update parameterization, but I'll tell you why you should use it in the next paper.
Gotcha. The motivating question, or the motivation for that question for me, was just that my intuition that I got from reading the like the derivations of the maximal update and why the other parametrizations fail was that essentially it's a matter of gradient flow. Like either the gradients all get soaked up by the top layer or they don't make it all the way to the first layer. And so that those are problems that you can imagine. Obviously, I mean, constants are important in that case. It's really just a scale between the first layer's gradients and the last layer's gradients. It's not a difference of like 0 versus non-zero versus infinite. And so that's the kind of phenomenon I was trying to get at with that question.
Yeah. So maybe concretely you're asking, perhaps in practice it's okay or maybe even beneficial to have imbalance between the gradients of different layers?
Yeah, I think that's one way to put it. Yeah.
Yeah. So that's a good question, and I believe that that's probably a valid question, and that's probably true in some cases or many cases. It's an empirical question. I think that can be looked at. Of course, now, like in the context of this paper and infinite width limits, of course, um, I think it doesn't make sense, right? If you, for example, you have a 3-layer neural network, but you parameterize it so that in the infinite width limit, your first layers just don't move. Then it's kind of a shame that you have all these parameters, you didn't actually use them. So, um, so while I agree with your sentiment that maybe the imbalance helps, the way I will implement this imbalance is actually to parameterize things in the maximal update framework, but you have constants that you can adjust so that you can adjust how much gradient is going to the first layer versus second layer, rather than putting them in a standard parameterization where when you go to infinite width limit, the first layer just don't learn at all. Like you can essentially leave money on the table if you use any other kind of parameterization.
That makes sense. Question from the audience asking about the intuition in the second backward pass with SGD and how that's different. And in particular, is there a way to think of what's going on, the difference in the distributions as being something like a prior or something like that?
Okay, so let's go back to that slide. Something like this, I guess. Okay, so the question was how to understand the backward pass and if there's a prior, it corresponds to some kind of prior.
Yeah, the question here, I'll just read it out. What's the intuition behind the second backward pass in SGD, and how are the Gaussian process utilized here? I think that might be a bit of a confusion, perhaps as priors.
I see. So I would say that I'm not using really anything about the Gaussian process here. So in particular, like I mentioned very briefly at the end, if you're in the feature learning limit, then initialization, you have a trivial Gaussian process in the sense that your variance is 0. You have a delta distribution at the 0 function. So I'm not using anything about the Gaussian process. I am using the fact that U and V are Gaussian initialization with variance 1/n. Yeah, in terms of intuition for the backward pass, here I'm not using anything special. Like here, I'm just literally doing, I don't know, like manual derivation of backprop. Like there's nothing complicated here. So the statement that the gradients of the second layer is first layer weights times the loss derivative times the input. This is just straightforward from backprop. If you do backprop manually, this is what you get. Very, very straightforward. And as soon as you have this identity, you can see that because like this blue, the first layer blue weights, they're essentially copied into the second layer gradients, and because these two scalars are roughly deterministic, you have approximately ID coordinates in this gradient, and similarly for the first layer, and then you can kind of iteratively push forward this observation to every future step in the training process. I hope that answers your question.
Yeah, and there's some more questions. One, are there any punchlines with regard to sparsity here? So there is a paper in the last ICML that talked about like transfer with the neural tangent kernel and sparsity.
So I think I've seen that paper, but I don't remember exactly what it is. So I guess so I would say the following. I think a lot of papers nowadays they do experiments on CFR10, but my point of view, like especially after this paper, is that that's not a good data set to do experiments on if you care about feature learning, because kernels do so well on it that like whatever you do on that, like this includes for example, new architecture search, whatever you do on it, it's kind of like you're not, in some sense, you're not isolating the effect of feature learning. Like so, for example, if you were to do architecture search on ImageNet or like do pruning on ImageNet, I think that's a lot more meaningful in the sense that in the CFAR10 case, when you try to induce sparsity, yeah, it suffices to just approximate the neural tangent kernel, and from like the sketching literature, whatever, there's a lot of these um, I guess like projection literature, which essentially just deals with sparsity. You can do a lot of things with that by just try to approximate NTK from a very just try to approximate using sparsity, using sparse weights very efficiently. You can get pretty good performance on these smaller data sets. But as soon as you go to larger data sets, I think these things won't work because you can't just approximate a fixed kernel. You essentially have to you have to find the right architecture to do the right feature learning. So I don't know. That was a rambling. I'm not sure if I answered your question.
It looked like, yeah, they responded in the chat that they like the answer.
Okay, great, thanks.
One question I wanted to ask was about computing all of this stuff, because you mentioned that you made use of that construction that you showed in order to do the word to calculations. And then there's also some sections where you talk about the computational scaling, and it seems like it's really unfavorable. So I'm just curious, what thoughts do you have in that direction in terms of actually like starting to use infinite width networks?
Yeah. So we'll have papers later on about this topic. But the gist is that kind of like in Bayesian literature, exact base is essentially intractable. You can't do it other than the simple cases. But I mean, there's still like entire industry academically behind it. And the gist there is that if you're creative, you can approximate the Bayesian inference using some clever ways, right? And that strikes a middle ground between efficiency and the optimality of inference. And in this case, it's very similar. You can come up with different approximations to the infinite width limit, which is not as trivial as just training a really wide neural network, but still kind of like goes part of the way to the infinite width limit. And you can also think about different kinds of limit to take, and so on and so forth. So there's a lot. If you're creative, you can do a lot of things in this area.
One thing it seemed to me from reading through the way that you were doing the actual calculations was that the tricky parts are evaluating a bunch of expectations for correlated random variables. So it sounds like essentially the trouble there is going to be doing efficient integration rather than doing like efficient and effective derivatives as you have in like normal finite width networks?
Yeah, so so generically speaking, right, like if you have just some kind of computation graph, you want to just take the infinite width limit of that, yeah, you're gonna end up with some really nasty integrals you want to solve. So if you want to have a black box limit taker, then you need to have a really, really good integration solver. But of course, like what I just said, if you just care about a very specific case, not a black box setting, like I just want to train, I don't know, like infinite width bird, like where the infinite width could be some approximation of infinite width. Maybe I can come up with some approximation of it that works pretty well and doesn't have to do this black box integration solving. You know what I'm saying?
Yeah, no, I see that. Though there was also a mention that the correlation structure itself can be very complicated. I don't remember the exact details, but that it can become like uh
Yeah.
like an exponential number of polynomial terms or something like that.
Yeah. So that's another difficulty, yes. But the answer is the same. If you're creative, you can ameliorize those problems.
Yeah, no, it sounds like a really exciting direction for future work, I think.
Yeah,
Like
I
being able to
definitely
do.
encourage people to think about how to do those approximations. And I mean, I really think the analogy with the base case is very similar. It's really apt.
Mhm. Yeah, yeah. There's a I guess, yeah, my interest in neural networks partly developed because I got interested in like Bayesian inference, found out about how intractable exact Bayes on graphs uh, was not that enthused by the approximations, and then ran into the arms of neural networks as a way to do, effective machine learning
Yeah,
without running into those problems. But
yeah. Now you can kind of go a little bit back, maybe.
I've been sneakily drawn back into the fields of integration and inference. That's it. Yeah. I guess one last question, I guess, before we go here. So with finite width networks, when you increase the number of parameters, you often have to worry about overfitting. So is that something that we don't expect to happen with infinite width due to something like the double descent phenomenon, or like to what extent do you have to worry about overfitting in infinite width networks?
Yeah, this is a very, very good question. So the short answer, I believe you need to take into account overfitting. Um, so in particular, in contrast with the kernel case, right, where in some sense, like your there's some inductive bias. I guess so does the feature learning case, but in the kernel case, it kind of like in some sense the capacity is kind of fixed in some sense. I don't know, like very intuitively compared to feature learning. Like feature learning, there's more wiggle room. You can learn more things, but of course you can also overfit more things. So you will run into overfitting for sure. Like for our experiments, um, we have weight decay on, and that like essentially that means that we didn't run into the case where the wider neural networks actually do worse on the evaluation. But in general, I think this is true that you need to take into account overfitting, how to take care of overfitting in the wider neural networks. With that said, in the modern trend of training larger and larger neural networks on larger and larger data sets, with the prime example being BERT and GPT and so on, we're actually not at the point where the model is large enough to actually overfit the data set significantly. So in that sense, if you're going in that direction, I think we don't need to worry too much about overfitting at this point. Just because like the data is so much larger than the possible model we can train. But yeah, for smaller things, if you care about something like CFAR 10 size, or even when you fine tune BERT on downstream tasks, the small data sets, you're gonna run into a lot of overfitting. You have to really be careful about regularizers. And if you write papers, that for glue or super glue, like fine tuning on the smaller data sets is all about regularization. So in that sense, without even going to infinite with limit, for large neural networks, you're going to run into this issue.
Mm-hmm. All right, so that's all the time we have. So I'll let you go, Greg, and our audience. Thanks for coming and presenting your work. I'm really excited to see where this goes, where people take these, start coming up with smart ways to approximate this, calculate this, and make use of this as a new tool in our toolkit for working with neural networks.
Yeah, thanks, man. Yeah, like you, I'm very excited about this work, and I'm very excited to see what the community does with it. All right. Thanks, guys.
Mm-hmm.
See you later.
Thanks, everyone, for coming. Take care.